Hello and welcome to the Daily Space for today, December 12th, 2018. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. Today, I'd like to start off by reminding all of you that if you miss an episode, for those of you who are watching live here on Twitch, you can always catch these episodes later in the day over on CosmoQuest's YouTube channel, which should be linked below. So, you have no excuse for not knowing what's going on in the world of space, science, and astronomy. Now, for those of you watching over on YouTube, welcome. Please click that subscribe button below. And if you're ever around at 1 p.m. Eastern, go ahead, catch us live over on Twitch at twitch.tv/CosmoQuestX. Now, today we have a variety of interesting stories, mostly coming from the solar system. This is, after all, the week that the American Geophysical Union is meeting out in Washington, D.C. That's where all the cool kids are hanging out, but I'm here at home because I have bronchitis, and I'm not going to be that one person in the audience ruining it for everybody else. But we still have all the news to bring you from what's going on out there in D.C. Now, our first big story of today is one that I'm actually bringing you a Twitter video because I couldn't find this video anywhere else. This is a video showing us a bit of the surface of OSIRIS-REx. Roman Tankanenko is an amateur astronomer who's been downloading these images and working to piece together the best videos that he can. You can see all the places that he's giving credit to. Let me rerun that video. So this is a zoom in compilation of images strung together, and you can see that Bennu is just one heck of a boulder covered world. Now, beyond just this particular piece of the solar system, we have a number of other pieces of news to bring you today. Our next story is one that involves a bit of light matter and a bit of dark matter and a whole lot of controversy. There's recently been discovered a number of distant galaxies off at about 10 billion light years away from Earth that, or more accurately put, away from our Milky Way galaxy. And these very distant galaxies that we're looking at as they appeared in the early universe, these galaxies don't seem to have the amount of dark matter that we'd expect. They instead seem to be made largely of normal luminous matter, stars, gas, the kind of stuff we can see with a telescope. This had led some to theorize that maybe galaxies out at a distance of 10 billion light years, maybe, just maybe, they didn't have the expected amount of dark matter, and dark matter is the kind of thing that galaxies add later on in life. Well, we have new results to bring you that come from a pair of different telescopes. This particular image is one that was obtained and processed by astronomers at the University of Texas, Austin. This is work being done by a graduate student, Patrick Drew, and his advisor, Professor Caitlin Casey. In this particular system, we have red light is images of dust as it was observed by the Atacama Large Millimeter Array, and blue is images that were taken with the Keck telescope in optical light. Now, in looking at this system, we have a galaxy that's seen pretty much edge on. And this allows us to very accurately measure how the material is moving as it sweeps round and round this particular galaxy. And what they found is the velocities of the dust and the velocities of the luminous matter that we were able to see all traces out that this particular galaxy seen 9 billion years ago. So it's 9 billion light years away. Its light has been traveling to us for 9 billion years. This galaxy has the amount of dark matter that we see in our local universe. It seems to indicate that while there are weirdo galaxies out there that don't have the amount of expected dark matter, those are weirdos. That, in fact, galaxies all the way back to the earliest days have been rich in dark matter, and the dark matter ratios that we see today are reflected in the early universe. Now, it's going to be interesting to see exactly how things play out as we get more and more galaxies observed. Back in the early days of astronomy, we used to say that if you saw two things, it was a trend. Well, in this case, we just have one data point for lots of dark matter, and we have a few data points for lots of not dark matter. What are we going to see as we add more galaxies to our data set? Time will tell, and this is one of those things where we eagerly await more observations from ALMA, Keck, the Very Large Array, and hope someday maybe to have a James Webb Space Telescope helping to add its data to this story. Now, continuing our journey through the universe, we're going to come a bit closer to home. In this particular case, we have an image of a very peculiar, or I guess very violent, binary star, Pear. This is the system R Aqaurii. This is a system that any of you can go outside and observe in your own backyard. Now, you won't see this kind of detail. This kind of detail, it requires the Very Large Telescope down in South America, in Chile. This image is the highest resolution image ever taken of this system. This system consists of one low mass, large radius Mira variable star. This is a red giant star. Thank you, KB Orut, for the subscription. Thank you so much. This particular binary star consists of a huge radius, low mass Mira variable star. These red supergiants are stars that are in the final days of their life. And at this point, they are very slowly pulsating over a period of roughly a year, expanding and contracting in radius, changing in brightness as they do this. Their outer atmosphere isn't that different in thickness from our own Earth's atmosphere, and they glow a deep, deep red in the sky. Mira itself, which you can see naked eye, is the prototype for this class of variable stars. Now, orbiting alongside this massive Mira variable is a massive in mass, tiny in radius white dwarf star. This is a star that has mass not too different from the mass of our own sun, can be a little bit bigger, but not too much bigger or it would collapse into something else. This white dwarf star has a mass roughly that of the sun, collapsed down into pretty much a crystalline structure, the same size as our Earth's moon. So you have this little tiny, physically, radius-wise, extraordinarily dense object orbiting round and round this low mass, massive radius, pulsating star. This weird scenario allows that high density white dwarf star to get close enough to that giant radius, lower mass, supergiant star. I know the names are confusing. And strip off its mass. What you see in this image is the jets of gas that have been strewn off and cast out over time. You can see down in the center two different blobs of light. What's happening here is as the white dwarf star cannibalizes, strips material off of its companion, that material gets cycled inwards towards the white dwarf star. It piles up on the white dwarf star surface, and over time it gets dense enough that it's able to undergo massive thermonuclear reactions, exploding like so many nuclear bombs on the surface of the white dwarf. Over and over, this happens, having what are called nova, not supernova, but nova events where the entire system massively brightens. Exactly how all of this happens, we can describe with theories, we can describe with computer models. We know that what is happening is the Myra variable is gravitationally not able to hold on to its material, that it's doing what's called filling its Roche lobe, which is this equal potential surface that is teardrop shaped. And at the end of the teardrop, the material is overflowing, getting gravitationally pulled over to the white dwarf. That material is spiraling in. We know the details with words and theories and models. This is the first time with this image that we're able to really start to actually see the details of what's happening in the system. The title on this is Dancing with the Enemy. There is a new paper coming out, and I, for one, really look forward to understanding how our theories have to change now that we're able to directly image some of the details of what's going on in this, in this cataclysmic variable system where a white dwarf is eating its companion. Now, to move on to something a whole lot closer to home, I have a story of the InSight mission, which has landed itself down on the surface of Mars. Now, where InSight landed is so remarkably flat and so remarkably boring. Sorry about that. Where InSight has landed is so remarkably flat and so remarkably boring that they haven't been able to figure out where exactly on the surface that Mars InSight is situated. They know it's in this very flat, boring plane, but they didn't know exactly where in the very big, flat, boring plane. Well, I'm getting word from Emily Lakdawala that they have now high-rise images where they have located within the images our little InSight lander. We are all eagerly awaiting release of these images so that we can, there's just something strangely satisfying about being able to see these little spacecraft from space. So stay tuned for more information. And for now, I leave you with InSight's first selfie. They did have to digitally erase the arm that was used to take the selfie. But here you can see exactly how our little lander is situated down on the red planet. Now, a couple quick reminders before we go to questions. Starting tomorrow night, you can actually see stuff tonight, but it'll be better tomorrow night. If you go outside tomorrow night, we will have rising on the eastern horizon early in the evening the constellation Gemini, the Twins. Radiating out of this constellation throughout the night, peaking in the morning of December 14th. So this is an event that starts in the evening on the 13th, goes through midnight on the morning of the 14th. We have the Geminids meteor shower. This year it's going to be particularly good because we have particularly little moon. The moon will be setting early in the evening. So get yourself out, bundle up if you're someplace cold, don't get sick watching meteorites, and go catch some shooting stars. This is an event that is brought to you by 3200 Pantheon. This is a comet asteroid thing, otherwise known as a dead comet or an asteroid with comet-like features. This little object orbits the sun every few years, leaving behind a debris trail that our planet is lucky enough to get to sweep through. And as we go through that debris, it hits our atmosphere and burns up in the process. Those burning up fragments of Pantheon, that's what we see shooting through the sky. This is nothing to be worried about. We're talking about grains of dust and maybe pieces as big as a pea. Whatever you see, it will be beautiful. And for those of you who are visually impaired, this is the kind of event that you can also enjoy by tuning an AM radio to a station somewhere between the stations. So find yourself the clearest patch of static you possibly can. And in that static, you will periodically hear whistles. Those whistles you hear are bits of debris reflecting back radio stations and Doppler shifting the signal to be something that you're able to catch for just a moment. So go out, watch, go out, listen, and enjoy yourself some Geminids. This is going to be one of the best meteor shows of the year, we think. And to look just a little bit further ahead, we have coming up December 22nd and 23rd, 40 hours of science for science. This is our CosmoQuest. Thank you so much, Trekker Kev, for the bits. Thank you. This is our big fundraising event of the year. As you may know from past episodes, we'd been warned back in August that we might be getting a funding cut due to James Webb cost overruns, due to changes in how NASA funds citizen science. And we didn't just get a cut, we lost our largest grant. And we had this happen at a time that I was switching between two different institutions. Thank you, Star Song. So CosmoQuest is now starting January 31st, being led out of the Planetary Science Institute. And all funds brought in through this Hangout-a-thon will be going through our new home. And this is our chance to, well, keep our staff paid for a little while we find that next big grant that will keep CosmoQuest being your place to come and join us learning and doing science. You can learn more by visiting Hangoutathon.org. We can't advertise this event on CosmoQuest.org because of rules with our existing NASA funding that means that we can't try and raise funds to replace the funds we're losing until we've lost the funds, which would make it really hard for me to make payroll in January. I'm doing my part to support this by, I'm not going to accept any salary out of these donations. My salary is going to come from the grants that I'm able to find and bring in. Your donations go to help us, well, keep Susie able to help this community going while paying her daughter's tuition. It helps all of our students who are students. It helps us with all of our early career people. This is Tanner, who you've seen as Herleu here on our channel. It helps us keep everything going by keeping our people going. Anything you can give is greatly appreciated, and no donation is too small or too early. So, yeah, consider giving if you can, and check out Hangoutathon.org. I'm going to be adding details as I learn them. Expect a preliminary speaker, guest, plot for what's going to be going on to begin appearing later today. So that's it for this episode of The Daily Space. Thank you all so much for joining me. I'm going to answer your questions in just a moment. I'm sorry, my dog has taken great offense at someone delivering things. Thank you, Paranor. I'm going to mute for a moment. So just as a friendly reminder, we are CosmoQuest's channel here on Twitch is a collaboration between the Planetary Science Institute and Youngstown State University. Go ahead, give us a follow to find out whenever we're going to go live. We work to bring you the daily space. We bring you rocket launches live as they happen, as well as other special events related to astronomy and space science. On Sunday, thank you, Veronica Cure, for the bits. On Sundays, we have Astro office hours with Annie Wilson. And in the new year, we're going to have a whole lot of new things going on. So give us a follow. Keep up with everything. And as always, we are sustained through your subscriptions and your bits. Thank you so very much. So if you can go ahead and at me in the chat, I will answer as many of your questions as I can. It's just going to take me a moment to figure out where I put the chat. Oh, okay. That's you can bring it here. I got flowers. They are apparently just enough that they're in color that they are getting blue screened, green screened, whatever screened, but thank you, flowers. So yes, excitement. And there's a balloon attached. So yay. Okay, going to go answer questions while coughing at you. Sorry about that. So I have coming in from Stormer Joe. How do they clean a probe of all microbes when sending it to land on objects in the solar system? A whole variety of different things. It depends on what part it is they're trying to clean. Some things get damaged by alcohol, so you can't use alcohol. Some things get damaged by radiation. Thank you, Decker KT. Dixer KT? I'm not sure how to say your name, but thank you. Different things get cleaned in different ways. It's a combination of heat, radiation, just cleaning solution. All the pieces get cleaned in the ways that are safest for the particular piece and deadliest for anything that might be on it. At the end of the day, we can't get things completely clean, but we do the best we can. Yes, Hanny's Vorverp. There will be 3D information. They are already working on, of Bennu, they are already working on preliminary shape models. And I believe we will be getting all the information necessary to do your own 3D printing of these things in the days to come. So Paranor, read the dark matter story, is asking, could that indicate that dark matter is something that came about after the universe cooled a bit? Not so much. Well, I mean, everything came after it cooled a bit. It depends on what you mean by a bit. When our universe first came into existence, it was so hot that everything, even the dark matter, was pure energy. Over time, that energy, thanks to E equals mc squared, transformed into matter. Some of it luminous, some of it dark matter, or more accurately, some of it baryonic matter that interacts via normal forces, including the electromagnetic force, and some of it dark matter, which is like, I'm not going to interact with the electromagnetic force. It doesn't reflect or emit light, and we only see it through its gravitational interactions. All of our models of how the first large-scale structures formed in the universe required there to be cold, dark matter present in the universe at this time. So this means stuff that wasn't moving at extraordinarily high velocities. Otherwise, we couldn't have stuff forming at the rate it formed. So we had to have dark matter in the early universe to get the present day universe with our understanding of how the physics worked. So yeah, it's a whole lot of chicken and the egg problems. So Hanny's Vorverp is asking, has there ever been large chunks of stuff that came from a meteor shower? So one of my favorite things that may have happened historically, and we're not entirely sure about this, is there are a few not totally well accepted papers out there indicating that part of what led to the collapse of the Bronze Age and end of a lot of the civilizations out in the Middle East was a impact event that would have been caused, I believe, by Comet Enki having broken up. There's multiple chunks of comet, of the main Comet Enki, a bunch of different stuff in a similar orbit. And there's some papers indicating that at one point we went through the tail right after the comet went by, and there was debris, and the debris did bad things. We did an episode of Astronomy Cast on this at one point. So go ahead and search for Bronze Age on Astronomy Cast, and you should be able to find that episode. So astronomycast.com. Looking to see what other questions we have. Fenring is asking, would it be possible to produce a good simulation of a white dwarf red giant pair based on the captured image? So I think what they'll end up doing is taking existing models and tweaking the models in a bunch of different ways to try and replicate what's seen in the image. We have the models. It's just a matter of getting the models to replicate what we see. This is something that we're used to doing with galaxy interactions, where we run galaxies through various simulations and then fly around the simulations at different points in time to try and figure out where you have to be to recreate what we see on the sky. Now we're just going to have to do the same thing here. Thank you for the links, Susie, and thank you for trying to find it, Paranor. So Hanny is asking, is there a way to know how many galaxies could have formed in low dark matter areas? I don't think we're there yet. I think we need more data before we can begin to figure these things out. One of the things that still needs to be understood is what was the decoupling ratio? So how much of the time did you have dark matter by itself? How much of the time did you have luminous matter by itself? And how much of the time did you have the two strongly coupled with where they're located in space? We're now starting to learn there are systems without dark matter, and there are systems that are just dark matter. We need to figure out more about how these different things are distributed on the sky. So, other questions? I'm going to drink my coffee while you type in any additional questions. So Hanny is asking, are the areas without dark matter spinning slower? Yes, this is actually how we identify them. If you can look at a galaxy and you see all the stars and gas moving in orbits that don't require non-luminous matter to be there, this means they're orbiting slower. If you can see these slower orbits, this means you don't have dark matter. You add dark matter to a system, it increases the total mass of the system, which increases the orbital rates of everything in the system. So you have things orbiting faster and faster the more dark matter you throw into a system. Yeah, Paranor, Star Trek totally did it wrong. I agree. So Bill Nash is asking, how long do you need to observe an object like that to make that measurement? Okay, Bill, I'm not entirely sure if you mean the R Aqaurii image or the dark matter image. I'm going to pull both up to remind everyone of what we're looking at. Let me switch screens. So here is the image of R Aqaurii. This is our binary star companion, and here is the dark matter galaxy, or dark matter and luminous galaxy that's located 9 billion light years away. in both of these systems, I'd have to look up those numbers. Let me see if I have those in the papers on my screen. So R Aqaurii, the binary system right here, is just 650 light years away. And the key to getting this image was they were using the massive telescopes that you can string together down at the Atacama Large Millimeter Array system. Sorry, I said that wrong. They used the Very Large Telescope, which is the VLT. This is a system of 4 massive telescopes that, again, can be arrayed together. Because this is fairly nearby, it may not have needed that long of an exposure. I'm not seeing it listed here. My guess would be it's on the order of nights. Let me click over to the research paper and see if it says. So they have 25 milli-arcsecond resolution. That means, so an arcsecond is pull out a piece of hair, hold it at arm's length, look at how wide it is held at arm's length on the sky. That angle is 1 arcsecond. So take that, divide it by 1,000. 25 1,000ths of a hair's width at arm's length is the resolution they had in this particular image. Oh, they're telling me everything except for the observing time. Okay, here we go, the data. You now all know that when I'm thinking, I curl my lips. I'm going to dump the link into the chat and let all of us read this on our own after the stream, because I'm realizing this is very boring to watch me reading a research paper. So here's the research paper. Yes, this is adaptive optics fenring that they were able to do this. So there's the link to the research paper on the red giant and the white dwarf. So I'm sorry to ruin your day with science. I can't tell you how many times I've had similar experiences of, oh my God, this is cool. I'm going to read all of this. And then for the dark matter paper, let me go ahead and drop this in as well. And Susie will be adding all of the show notes later on over on YouTube and on the VOD that will be stored on this channel. Yes, Paranor, Chang'e 4 has entered lunar orbit. Who would have thunk a couple decades ago that China was going to be the next nation to, well, race out to explore the moon? So yeah, life is good. Oh wow, I hadn't seen how narrowly InSight missed its foot on that rock. That's kind of amazing. Dang. Oh. So Crispy Fried Man, who has a slightly traumatizing username, is asking, Voyager detected whistle sounds from Jupiter that they said was lightning. How did they know this? So we can see lightning on Jupiter. We can see how it flashes. Same thing with Saturn. I'm not sure exactly how they did it with the Voyager probes. I just know this is something that we've been able to recreate over and over. I think it may have been the characteristic radio noise created by the lightning. When we look at our own planet from space, we get all sorts of different signals that go along with the lightning strikes, as well as the flash of luminous light that we're all used to. So the whistles weren't the same whistles that we get from meteors going through our own atmosphere. The whistles were a description of something that was observed in non-visible wavelengths of light. I believe radio wavelengths of light. Yes, Stormer Joe, Chang'e 4 is landing on the far side of the moon, not the dark side, the far side, the side that is never facing our own planet, that is geologically radically different from the near side. There are some papers out there that believe that the reason the far side of the moon looks so radically different is, well, we believe currently that the way the moon formed is you had the early Earth, which was a bit smaller than the current Earth, and a Mars-sized object came in called Theia, collided in with the Earth. The two cores merged. They kept some of the heavier, kept most of the heavier weight materials, splashed out a lot of the lighter weight materials. Those lighter weight materials coalesced in orbit around the Earth into two separate objects, where eventually one of those two objects collided into the backside of the bigger of the two objects, leading to what we see today. Thank you, Paranor, for finding that. So do we have any more questions out there? I'm running out of voice quickly, but I probably have voice for one or two more questions. Okay, so I'm not seeing any more questions. Thank you, Ed Thompson. Thank you so much for the bits. It's really appreciated. So I'm going to prepare to rest my voice, and I will be back here tomorrow with hopefully a little bit more voice than I had today to bring you all the science that I can from the world of space science and astronomy. So as always, the Daily Space is brought to you by the Planetary Science Institute, working in collaboration with Youngstown State University. We are sustained by you. Give us a follow to find out when we're going live with all the various content we bring. We have the Daily Space coming most Mondays through Fridays at 1 p.m. Eastern. That is 11 a.m. Pacific, 6 p.m. London time. We also bring you live events as they happen, whether it be the landing of a spacecraft on another world or the launch of yet another rocket here on the planet Earth. We also have a variety of different office hours, and new programs will be starting in the new year. We are, as always, sustained by you. Your subscriptions really matter, and every bit really helps. Thank you so much for joining me, and wherever you may be in the world, have a fabulous morning, evening, or afternoon. Thanks. Bye-bye.